So we went from having polynomial equations where we would solve by factoring and we would get real rational zeros. Then we moved on to solving by factoring and getting real irrational zeros. And now I'm just going to kind of prepare you for this. We're going to be factoring and we're going to be looking for real as well as complex zeros. So as far as the process of factoring, that's not going to change. We're still looking into what type of binomial or trinomial or polynomial that we have and look at and use the correct factoring technique. So for instance, in this first example, we're just going to work on these four. I basically cover everything that we need to in these four examples. In this first example, you can see we have a trinomial. So therefore, I'm going to want to look into this, factoring this into two binomials squared. So first thing I look at is I say, all right, remember in what we previously did, you can kind of forget about this being raised to, the fourth power and just think of it to the squared. But I obviously have been doing these examples, through these videos. I'm going to be like, all right, let's kind of move on. We know this is going to break down to to two binomials. So x times x, and then my last two numbers need to multiply to give me 4. So the two numbers that multiply give me 4, you could do 2 times 2, negative 2 times negative 2, 4, 1, negative 4, negative 1. Crap, this is non-factorable. That's not what I needed to do. This needs to be a negative. So there you go, mistake number 1. That needs to be a negative for at least the problem that I'm doing. So there we go, make first mistake. So this one's supposed to be a negative 4. And the reason why I could see that is because I know that the two numbers need to multiply to give me 4. So 1 times negative 4 gives me negative 4. All right, and I didn't mean for this to be non-factorable. I know which example I want to be factorable or non-factorable. But x times x does not give us x to the 4th. So what we need to do is just factor it like a quadratic and then just raise the powers. And again, your middle terms need to give you x squared, and as long as your last terms gives you that negative 4, we're good. And you can see that this factors multiplies out. X squared times x squared is x to the 4th. X times, x squared times 1 is x squared. X times negative 4 is negative 4x squared, and they give you negative 3x. So now, again, we're trying to find the 0, so I'm not sure why I set this equal. So now what we can do is let's just rewrite it. Why not? So now we're trying to find the 0, so you're basically finding the values x where this is equal to. Now this is not in our linear factorization. Do we have to write it? We have to write it as a product of linear factors. So this is not as a product of linear factors. So we have to further factor this down. Now the x squared minus 4, that's easy to factor, right? That's difference of two squares. The x squared plus 1 is probably, maybe as you initially started, might not be as obvious to you. So let's just go and use, even though we could factor this down, let's just use the zero product property to solve to find the zeros. And then what we'll do is, going from the zeros, we will go to the factors. So subtract 1, subtract 1. So I get x squared equals negative 1, and then plus 4, and I get x squared equals positive 4. So now, when I go ahead and introduce the square root, and remember, you have to include plus or minus. In this case, you can see I'm taking the square root of negative 1, which is our I, right, as our imaginary unit. So x equals plus or minus I, and here you get x equals plus or minus 2. Which again, guys, we already knew that answer, right? We already knew it was x minus 2 times x plus 2, right? You see, you just could have done that from there. So those are going to be all your zeros. And again, kind of going back to the fundamental theorem of algebra, you can see that we have 4 zeros, plus minus, plus minus. Only 2 of them are real and 2 of them are imaginary. But the other part of the question, I think, let me just make sure I had this right. Write the zeros, then write the polynomials as a product of linear factors. Okay. So now, if I want to write this as a product of linear factors, I would say y equals, and then now, if I have the zeros, I can write these as factors. X plus I times x minus I times x plus 2 times x minus 2. Okay. And there you go. There's your product of your linear factors. All right, so let's get on to the next one here. And the next one is a binomial. So immediately what I start thinking is difference of two squares. And even if it's written up to the 4th power, again, you got to think, can you take the square root? Is x to the 4th the square term, and is 16 the square term? And the answer is yes. It's just raised to a higher power. So this can be further factored down into x squared minus 4 times x squared plus 4. Okay, So then again, you can see we're back at that x squared minus 4, right? So I can factor that easily. And hopefully you can get to this point as well. I'm going to factor it without solving, but then I'll do the solving for the complex number as well. So if I wanted to write these as zero products, rather than doing the zero product property, I could just factor this, x minus 2 times x plus 2. And then if I wanted to factor this, notice I'm just going to solve in my head. If I was going to solve this in my head, I'd be subtracting 4 and then taking the square root. Well, I can take the square root of 4, which is 2, but it's going to be a negative 4, right? So therefore, this would be x minus 2i and x plus 2i. And again, I just want to notice, understand you have these complex numbers. You see how the conjugate exists. If I exist, negative I exist. Or if 2i exists, negative 2i exists. Now, if you are wondering how did I get that, I'll just solve it right here. Pretend, let's just set it equal to 0, use the zero product property. So therefore, you'd have x squared equals negative 4. And then you take the square root of both sides, and you have x equals plus or minus the square root of negative 4. Well, again, guys, remember you can take the square root, you can break that up, negative 1 times 4. So now the square root of negative 1 is I, and then you have 2. Or usually we just write that as 2i. So x equals plus or minus 2i. And then you have your, now that you have the zeros, you can rewrite them back as factors. So let's just go and write the sets formation of the zeros. So I have plus or minus 2 and plus or minus 2i. And again, using the fundamental theorem of algebra, we have 4 zeros and our degree is 4. So we're good. All right, moving on to the next one. Now we have another trinomial. Now again, we can't use the process that we used up here by just raising the powers because that doesn't work. You can't do x squared times x squared. It's not going to give you x cubed, right? You have to add the powers. And then plus, we can't just say, oh, well, x squared and x. Well, then your middle terms aren't going to combine because they won't be like terms. So immediately in this one, I noticed that they all share an x. So I'm going to factor out an x. So I factor out an x. All right, and now I look, okay, well, now this is factorable, right? Let's go and do the factoring. And then it's like, crap. What two numbers multiply to give you 5, add to give you negative 2? That doesn't exist. So therefore, if I set this equal to 0, I can basically say, oh, x equals 0, and then 0 equals x squared minus 2x plus 5. Well, that's a 0. That's a real 0. Good, I got that. But how am I going to solve here? What do I need to do here? It's non-factorable, so therefore I have to go back and use my lovely quadratic formula. So again, if I'm set my equation, set equal to 0, and I'm trying to find the values of x that make that true, the values of x that make that true is on the quadratic formula. And let's just see, here's your a is 1, b is negative 2, and c is negative 5. So let's go and plug them in. So I'd have opposite of b plus or minus square root b squared minus 4 times a, which is 1. Oh, that's a 2. Why was I thinking about that? I messed that whole thing up. Let's redo that. So I have opposite of b, which is 2, plus or minus the square root of b squared, so that's negative 2 squared, minus 4 times a times c. And that's all over 2 times a, which is 2 times 1. Okay, now I'm going to kind of work vertical here just because I want to keep this area for the zeros. So therefore, I'm going to have 2 plus or minus. Let's simplify this. Negative 2 squared is 4. And therefore, this would be, so it's 4 minus negative 4 times 5, so it's negative 20 all over 2. Oh, I picked some nice ones, so you get that. So therefore, this gives you a negative 16. So therefore, I have, let's write it down here. I'll have more room. X equals 2 plus or minus the square root of negative 16 divided by 2. And then, ladies and gentlemen, I can simplify that to 2 plus or minus. That's going to be 4i. Square root of 16 is 4, and then negative 1, so that'd be 4i. Divided by 2, and then you can divide the 2 into everything, and you get 1 plus or minus 2i. Whew. But that's a little bit easier. Those are your zeros, right? So if I wanted to write this as a linear factorization now, all right, remember, these are your zeros. So you could say like x equals, let's write that out. Let's write your zeros. So your zeros are x equals 1 plus 2i, x equals 1 minus 2i, and x equals 0. These are your zeros. So remember, when you're writing the linear factorization, you're basically setting them equal to 0. So you're subtracting a 1, subtracting a 2i, subtracting a 1, adding a 2i, and then you could subtract a 0 if you wanted to, but you don't really need to write that. So I'll just leave that as x instead of x minus 0, which is unnecessary. But these zeros look like this. X minus 1 minus 2i. And then this one would be x minus 1 plus 2i. And again, even though the x minus 1 is the same, notice the complex conjugate. It's negative 2i, positive 2i. All right? And again, does this follow the fundamental theorem of algebra? We have 1, 2, 3 zeros. 1 is real, 2 are imaginary. And we're all good. All right, on to the last example. And you can see here we have a polynomial with 4 terms. So immediately I'm going to think about grouping. So we group the first 2 terms and group the last 2 terms. I say, all right, how can I, factor this? Not how can I factor this? I know how to factor by grouping. What GCF can I pull out from each of these groupings? So, and again, we're trying to find the 0. So let's just set it equal to 0. So here you can see that they both share a 2x squared. So when I factor that out, I'm left with a 2x minus 1. And then again, now I'm looking for this common factor that's going to give me the 2x minus 1. Thankfully for this one, it's not too bad. It's just going to be a 2. So therefore, when I factor a 2 out, I'm left with a 2x minus 1. Okay, and again, remember the factoring by grouping is kind of like 2 steps. You have the first step, factoring out the GCF, and then you have the second step of factoring out the GCF again, but of these bigger expressions, right? These are bigger expressions here. And you can see these both share a 2x minus 1, so I factor out a 2x minus, So I factor out a 2x minus 1, and now I'm left with a 2x squared plus 2. Okay, so then now you could try factoring this if you wanted to, or we can just go to the 0 product property, right? We have a product and we can solve for it. So I'll just set each one equal to 0 using the 0 product property. And then I have 2x squared plus 2 equals 0. Oh, it would have been easier to factor out the 2 from the beginning, wouldn't it? Well. So add 1 divided by 2, x equals 1/2. Here I could factor out a 2, or you could subtract 2 and divide by 2. Either way, or I prefer just to factor out that 2, because when you factor out the 2, you can divide it out, so you're left with x squared plus 1 equals 0, subtract 1, x squared equals -1, square root, x equals plus or minus I. Kept the numbers fairly simple for you. So if I'm going to write this as a linear factorization, I have 1 real 0 and then 2 imaginary. So that would be y equals x minus 1/2. Ooh, I don't want to write the x minus 1/2, right? You can see here, you could write it x minus, but then when you multiply, you're not going to get that original polynomial. So here is that factor, which I already have here. So that's good. Let's just keep it just like that. So I keep that as 2x minus 1. And then this factored form is going to be the x minus I, x plus I. And then obviously you still have that 2 that got factored out of everything. So let's just erase that and let's keep that clean. Let's clean that up a little bit. So y equals 2, right? Because really when you multiply those out and multiply everything by 2, you're there. And therefore your zeros then, notice that 2 is not a 0, so don't include that. But your zeros are going to be 1/2 and then plus or minus I. And again, you could even check, even if you're like confused, how many zeros do we need to have? 3, right? And you can see we have 2 imaginary and again 1 real. So that's kind of the importance of that. So not always are polynomials going to be factorable. Where you can factor them to find the real zeros. You can see here the quadratic formula comes up. Like a lot of times we can factor across imaginary zeros using the square root method, but sometimes we have to use the quadratic formula. And or not always is polynomials going to be factorable. And so what we'll learn later in this unit is, what do we do when it's non-factorable at all? But next, we'll just kind of take a look at now the sum and difference of two cubes, which is basically a special case of a polynomial, very similar to the sum or to the difference of two squares, but for solving, it's going to come a little bit more application. So let's that's what we'll get into right now.